All right, lads and ladies, welcome back to Honors Calc 1. Today is Katie's student teaching day, so I ask that we all be polite, kind, courteous, take good notes. I've reviewed the videos she's prepared for us, and they are genuinely good videos on antiderivatives. I think you'll get everything you need out of them. There's a few things I want to talk about before we get into that. And the first thing has to do with the exam grades. Where is my, oh, this was really cute. Sometimes people write math problems without really thinking about the implications. So here they show 4 people all able to look at each other with a distance of 1.5 meters in between them. This is impossible in 2-dimensional space as they've drawn it. And in 3-dimensional space, the only configuration that works is if everybody is exactly 1.5 meters tall and they're arranged, half of them upside down and half of them right side up. So the title is, oh, so this is what they meant. I thought that was pretty cute. Thought you might like that. But having said that, I've got some news about the exam grades. They weren't that good. So I put a pause on grading your guys' tests after grading my non-honors class, where the average was around 45. And I'm thinking what I ended up doing is curving theirs. I've never done that before. I've never in my life curved a test. I've always been deeply, deeply against it. So I'm reworking my rubric as I grade your guys' stuff, and I'll have your final grades for exam 2 in just about an hour or so after class ends today. So if you're having a hard time making any sort of important decisions using that exam grade, I do promise you it'll be in there a little bit later today. I just wanted to stop and rethink how I was grading things based on the results that I got out of my non-honors class. You guys being the honors class, I do trust things are a little bit better. But I just wanted to make sure that the grading approach I was using was appropriate given all of the bullshit with COVID and everything. So there may end up being a curve. If you've already gotten your grade, I did grade a few of your guys' tests before I decided, wait, I'm going to stop and rethink this. That grade may not stand. I may end up either regrading it with a new rubric or applying a curve like I did to my earlier class. And I just wanted a moment to think before following through with that. So I apologize. I know you guys all want those grades. They'll be in very, very soon. I promise a little bit later today, but trust me, it's to your benefit that we stop and think a little bit about this. I'm grateful that there isn't as much cheating going on as there used to be, but it seems that the last few semesters of COVID math have kind of stung us in the ass. So I just want to take a second and make sure we're being fair. The other thing I need to share with you before we get into Katie's lectures today is one remaining theorem from section 5.2. So one last theorem from 5.2. If f of x is integrable, meaning it can be integrated and bounded below by little m, I shouldn't do this, is bad grammar, and bounded above by big M on the interval closed interval from A to B. And remember, in particular, any continuous function would have this property. Every continuous function is integrable, and every continuous function attains an absolute min, which would be a good lower bound, and an absolute max, which would be a good upper bound on any closed interval. So if you have, for example, a continuous function on a closed bounded interval, or even a discontinuous function that is still integrable and has both a lower and upper bound, then little m times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to big M times b minus a. The proof here is simple enough and insightful enough that I want to share it with you. It all just comes from a picture. So let me draw here for you. a kind of generic looking f of x. Maybe I'll imagine a is over here and b is over here. Then, as we have discussed, the integral from a to b of f of x gives you the exact area bounded by this curve. Gives you this exact area. I'm not an artist, I apologize for my bad drawings. But we do need this to be somewhat good here because I'm going to add in some other areas in different colors. All right. So we know that this pencil shaded area is the object in the middle, right? The area bounded by f of x and the x-axis from a to b is the integral from a to b of f of x. What does it mean to say that little m is a lower bound, or bounded, that f of x is bounded below by little m? It means that the graph of f of x, at least between a and b, never goes below little m. So the sort of natural choice here would be to go for the absolute min of f of x on the interval ab. So this would be little m down here. And similarly, the natural choice for the upper bound would be to go for the absolute max of f of x on the interval ab. So this is the line y equals capital M. And what I want you to do now is think about a few little areas. You, of course, have the pencil shaded area there, which is the integral. I'm going to shade the area down here in purple. I'm going to shade the area underneath the blue function in blue. Loose definition of the word shade there. What we notice is that the purple area fits inside the pencil area, right? So the purple area has to be smaller than the pencil area. Well, what is the purple area? This region is rectangular. So the area that is shaded purple here is the height, which is little m, this little height, which is little m, times this width, which is b minus a. So the little purple area here is little m times b minus a. And because it fits inside the pencil area, it has to be smaller than the pencil area. So the fact that this purple area, which is little m times b minus a, fits inside the pencil area proves the first half of this inequality. And then the obvious thing is true about the blue area and the pencil area as well, right? This blue area is larger than the pencil shaded area because the pencil shaded area fits inside the blue area. So the blue area has to be larger than the pencil area by inclusion. What is the blue area? Well, it's also a rectangle, and the height here is capital M, and the width here is b minus a again. So the blue area is larger than the pencil area. The blue area is big M times b minus a, and the pencil area is the integral from a to b of f of x dx. So big M times b minus a has to be bigger than the integral from a to b of f of x dx. This theorem is very useful for estimating integrals when the actual normal work to estimate the integral is hard. Like you don't want to set up a Riemann sum. We're too lazy for that. I don't want to calculate like R10 or something. Or maybe it's hard because my function isn't just increasing or just decreasing to say whether R10 is an overestimate or an underestimate. This gives me some way to say this number is for sure bigger than the area without doing a Riemann sum. And this little guy gives me a way to for sure say this number is smaller than the integral without doing a Riemann sum. It has utility in a few different places, but mostly you'll see that you have a handful of homework problems that require you to just practice with this theorem. So let me show you the new homework. I published this yesterday morning, I think, because you technically had until today to finish last week's homework because of the exam. So quick preview of these homework problems. The first few are just the same shit as last week, using rectangles to estimate areas under curves. The big difference now you'll notice is that the functions are allowed to sometimes be negative, right? Here, this function doesn't live above the x-axis all the time. Here, the y values are sometimes negative. So the first two problems are exactly the same as last week. This is also very similar to something we talked about last week. Remember the xi plus xi times sine of xi thing that we wrote as an integral? Same shit going on here and here. So you're just getting practice writing those things as integrals. Numbers 5 and 6 have you using the definition of the definite integral. So lim n to infinity, sigma I from 1 to n, f of xi times delta x. Actually evaluate this integral. If you want to see the video where I solve this problem exactly, or solve this problem entirely, it's not exactly this problem, but a problem with different numbers like this, I'll post the video from my non-honors class this morning to your guys' section, but I don't want to get into Katie's time too much. But that's what you need to do here, and it's the same as the find the exact area problem that we talked about last week, where you use those summation formulas at the end and then take a limit. Problem 6, same sort of thing, only first you're going to do R8 to get an approximation, and then you're going to do the full sum. Problem 7 here, they ask you for the integral from 0 to 6 of f of x dx. That's the area bounded by this function from 0 to 6. That's the area of this little region. Similarly, they ask you for the integral from 0 to 15 of f of x dx. That's the area of this region. And you're going to use geometry to find those. You're going to break that up into some triangles and some rectangles, however you want, to find all of these guys. Just remember that area beneath the x-axis, like stuff over here, will be measured as negative. Those are all things that we've talked about before. It's mostly just about getting you comfy with the notation of the definite integral. Here, this one is a lot like the problem we solved on Monday, where we had a region that was semicircular, and you needed to find the area. Same sort of shit going on here, and then again over here. So all of these are about interpreting the integrals as areas. The last few guys, these require use of linearity. Remember, we talked about those properties of the definite integral last time, where you can split up over addition or subtraction, you can pop out constants. And then this guy is about splitting up, the integral a to b is integral a to c plus integral c to b. You're going to use that property here. So these are all things that we've talked about before. I'm confident that you guys will do well on them, but if you do run into any issues or you're not sure what to do, come see me in office hours. The theorem that we just discussed is the theorem that is necessary to answer question 18, 19, and then these are back to more Riemann sum practice. Here, they're going to give you the sum and ask you to write it as an integral instead of going the other way. The remainder of the problems all have to do with antiderivatives, which is what Katie's lecture is on today. So I'm going to go ahead and hand it over to Katie. Katie, is there anything you would like to tell the class before I begin playing the videos?
I don't think so.
Alrighty then. So let me go ahead and get my stuff out of the way. And play Katie's videos. So make sure you take notes. Katie went through the work of recording herself writing these things, so you can take notes at an appropriate pace. Let's respect that by taking nice, clean notes from Katie's lecture here.
Today, we'll be going over 4.9, which is antiderivatives. First, we'll start with the definition, which is a function is called an antiderivative of f on an interval I if f prime x is equal to f of x for all x in I. And we'll write examples. So we can let f of x equal x squared. Now, we're going to simply get the antiderivative. And the most basic way to do this is to use this simple equation, which will look like, we can either write it like this, times x n plus 1, or we can write it as x n plus 1 over n plus 1. So if we apply this to the x squared, we'll get x 2 plus 1 over 2 plus 1, which will then give us 1 over 3 x to the third. So if f of x, capital F of x, equals 1/3 x cubed, then the derivative of that is equal to f of x, and f of x is equal to x squared. But we also have to realize that there can be a function, say g of x, that can be 1/3 x cubed plus something, say 100. That also satisfies the antiderivative, so that we could say g prime of x equals x squared, which equals f of x. So both capital F of x and g of x satisfy f of x. Therefore,
No, I'll feel you good.
both and g are antiderivatives of f, and it is also true that for any function of the form h of x equals 1/3 x cubed plus c, where c is a constant. So moving on, we need to recall something, the mean value theorem from 4.2. It states that if two functions have identical derivatives on an interval, then they must differ by a constant. So with capital F and another function, say g, are any two antiderivatives of f, then the following apply. F prime of x equals f of x, which also equals g prime of x. So another way to write this would be to subtract f of x from g of x and set it equal to c. So in other words, it would be g of x minus f of x equals c, where c is a constant. Now we can even rewrite this to make it g of x equals f of x plus c. Next, we have or this leads us to our next theorem. So our next theorem is if capital F is an antiderivative of f on an interval I, then the most general antiderivative of f on I is capital F of x plus c, where c is any arbitrary constant. And arbitrary just means unassigned or random value. Now, going back to our function of f of x equals x squared, we see that the general antiderivative of f is 1/3 x cubed plus c. By assigning specific values to the constant c, we obtain a family of functions whose graphs are vertical shifts of each other. In other and shorter words, if we assign specific values to c, the graphs will be vertical shifts of each other. The graph to the right proves this to be true. And this makes sense because each curve must have the same slope at any given x value.
Very nice. So let me pause here for a second. I have the second video queued up. I just want to say one or two little things. The basic idea behind antiderivatives is finding a function whose derivative is the given function. And Katie's description there of the power rule is very, very good. One other way of writing that, which might be useful to think about. So I just want to make sure we state it somewhere nice and clearly. The power rule remember, that's a statement about derivatives normally. d dx of x to the n is n times x to the n minus 1. It has an antiderivative version. Another way of saying this is that if little f of x is x to the n, and I want to undifferentiate it, I want to go backwards in the differentiation chain, instead of pulling down the power and subtracting the 1 from the power, right? Instead of reducing the power by 1 and multiplying by the old power, then an antiderivative, and we always use capital F or a capital letter for the antiderivative of little f, or the little letter here. If I want to undo the differentiation process, I want to go backwards through something like this, rather than reducing the power, I increase the power by 1. And rather than multiplying by the old power, I divide by the new power. It's exactly the backwards version of this. So this is the differentiation power rule. This is the anti-differentiation power rule. And if we're looking for the most general antiderivative, just like Katie said, we would slap on a plus c at the end, because the c will always differentiate to 0. And then Katie's argument to show why this is the case is perfect. If you were to differentiate this, the power would become n, because we would subtract 1 from it, and we would have an n plus 1 down here, which would cancel with this. So the derivative of this is this. And I think this is the neatest way to kind of remember it, that just like when you differentiate x to the n, the power goes down by 1, you multiply by the old power. When you anti-differentiate x to the n, the power goes up by 1 and you divide by the new power. So with that said, let me go ahead and start her second video.
Now let's try an example. Find most general antiderivative of each. So we'll start with A, which will be f of x equals sine of x. So to do this, we need to think of what trig function is sine x the derivative of. Well, we know that if we take the derivative of cosine equals negative sine x. Since we know that, we got to think about the patterns in sines. So if we take the derivative of negative cosine x, we get sine x, which would look like f of x capital equals negative cosine x. We can also check this by taking the derivative of f of x, which would give us f prime of x equals the derivative of negative cosine x, which is sine x. So an antiderivative of sine x is negative cosine x. We then need to apply theorem 1. So g of x equals negative cosine x plus c. That gives us the most general antiderivative.
So moving on from that, we can now go on to part B of this example. In part B, we will do f of x equals 1 over x. For this, think of functions that equal this when you take the derivative. So we can recall that d of dx, parentheses ln x, equals 1 over x. And we are familiar with this one. We also know that d of dx of ln absolute value of x also equals 1 over x. Now we need to find the intervals on which these functions apply. For ln of x, we know that ln of 0 does not exist, and it cannot be negative. So we get the interval of 0 to infinity, not including 0. For ln, absolute value of x, since the absolute value is there, we are allowed to use a negative, but 0 does still not exist. So for ln absolute value of x, the absolute is there to allow that negative, and everything except 0, which gives us interval negative infinity to 0, u 0 to infinity. So the general antiderivative of this would be capital F of x is equal to ln of x plus c1 if x is greater than 0, and it's also equal to ln of negative x plus c2 if x is less than 0. We need that negative sign there so that it can act as the absolute value. Next, we'll start with example C, or we'll move on to example C. So example C will be f of x equals x to the n, where n cannot equal -1. Will we use the power rule to discover an antiderivative of x to the n, like we used in the general example? Using that same equation, we would get that capital F of x equals x to the n plus 1 over n plus 1. And we can check this by taking the derivative of this function using the quotient rule. So then we do this by doing d over dx and writing the function x to the n plus 1 over n plus 1, taking the quotient rule, which would keep the bottom the same, which is n plus 1, then use chain rule on the top, which is n plus 1, x, n plus 1 minus 1, which will just give us x to the n, minus, take the derivative of the bottom, which will just give us 0, times, leave the top alone, all over the bottom squared. When you clean this up, you can see that n plus 1s on the top are squared, and it's times x to the n over n plus 1 squared. And those two will cancel out, and you're left with x to the n. So then, the general antiderivative of f of x equals x to the n is capital F of x equals x to the n plus 1 over n plus 1 plus c. You have to remember the c. We have to realize, though, that this is valid for everything n equal to or greater than 0. Since f of x equals x to the n is defined on an interval, if n is negative but not equal to -1, it is valid on any interval that does not contain 0. Because if you plug in 0 into x to the n, it gives you 1. So the interval would be -infinity to -1, u, -1 to 0, u, 0 to infinity.
All right, so I do want to make a quick comment here also. Katie's proof does work, but there's an easier path to proving this. So if we want to prove the power rule and we're feeling lazy, we can say that looking at the derivative of this suspected antiderivative should come out to little f, should come out to x to the n. And as she did it there, it does work. But we can do this a little bit quicker if we recognize that the n plus 1 downstairs is a constant. So here's the lazy proof. If you want to take d dx of x to the n plus 1 over n plus 1 plus a constant, first we would split this up as d dx of x to the n plus 1 over n plus 1 plus d dx of c. Of course, the derivative of the c here is going to be 0. And here, since the n plus 1 is a constant downstairs, we can think of this as 1 over n plus 1 times x to the n plus 1. And this, like we said, is 0. And now this 1 over n plus 1 is a constant, so he can come out front. This is 1 over n plus 1 times d dx of x to the n plus 1. The quotient rule approach there is valid, but I feel like this proof gives a little bit more insight into why the power rule looks the way it does. Because now you've got a 1 over n plus 1 out front. And if you differentiate this using the differentiation power rule, this power should come down. So you'll get n plus 1 times, and then you subtract 1 from the power. Well, n plus 1 minus 1 is x to the n. And then you can just cancel these two pieces, boom, boom. And you get your x to the n. There's nothing wrong with what Katie did. It's just a little bit more complicated than I think is strictly speaking necessary. The other comment I want to make here is on the natural log function. So we all know that, like Katie showed us, the derivative of ln x is 1 over x. And this is valid as long as x is greater than 0, because that's where the natural log is defined. So immediately from this, we see that if little f is 1 over x, then capital F would be the natural log of x plus a constant. But this again assumes that x is greater than 0. So the way we get around this is we say more generally, if little f is 1 over x, then capital F is the natural log of the absolute value of x plus c. And the absolute value there is just to handle the cases where x is not positive. So this is good as long as x is not equal to 0. And then the power rule, one more little comment on the power rule. The only instance where the power rule doesn't work is the instance where you should be using this instead. 1 over x is the same as x to the negative 1. So the thing that we needed to be non-zero here is n plus 1, which means this works great as long as n is not equal to negative 1. That's the case we need to watch out. So just to be clear, here's the power rule. And it works for all power functions x to the n, except where n is equal to negative 1. And if n is equal to negative 1, then you're looking for an antiderivative of 1 over x, because x to the negative 1 is 1 over x. The antiderivative for 1 over x is the natural log of the absolute value of x plus c. And here, this is the n equal negative 1 case, but you still need to be mindful of domains. So the requirement that x is non-zero is coming from a domain of this function. The original function here is not defined at 0, neither is the natural log. So with that out of the way, I will move to the next video.
This is a table that includes the function and antiderivative of that function.
You need to
In the book,
memorize this
they use
table.
the notation f prime equals f and g prime equals g. We should note that to get the most general antiderivative from ones like in this table, we have to add a constant like we did in example 1. So for example, it'd be like e to the x plus c would be the particular antiderivative of the function e to the x. I'll give a second. So we should also note that we often use the capital letter F to represent an antiderivative of a function f. If we were to begin with a derivative notation, f prime, an antiderivative is f.
Now, for example 2, we are going to find all functions g such that g prime x equals 4 sine of x plus 2x to the 5th minus square root x all over x. So we can rewrite this as g of x equals 4 sine x plus 2x to the 5th over x minus square root x over x. Cancel some of these, and we will get 4 sine x plus 2x to the 4th minus 1 over square root x. Now, again, to simplify and rewrite, we write g prime of x equals 4 sine of x plus 2x to the 4th minus x to the negative 1/2. So using the table or your knowledge of the antiderivatives, we then can solve for g of x. And we do that. G of x equals, we did sine of x earlier. So it'd be 4 times negative cosine of x plus, using the x to the n plus 1 over n plus 1, we can get 2 times x 4 plus 1 over 4 plus 1 minus, doing the same thing for this one, x negative 1/2 plus 1 over negative 1/2 plus 1. Now, to rewrite this and simplify it to get the final, we do g of x equals -4 cosine x plus 2 over 5 x to the 5th minus 2 square root x plus c. Don't forget the c.
So moving on, a differential equation is an equation that involves the derivatives of a function, and the general solution of this involves an arbitrary constant or constants, like in example 2. However, there may be some extra conditions given that will determine the constants and therefore uniquely specify the solution. We'll move on to example 3.
Find f if f prime of x equals e to the x plus 20 times 1 plus x squared to the -1. We need the general antiderivative, and we can start by rewriting this as f of x equals e to the x plus 20 over 1 plus x squared, which can also be rewritten as e to the x plus 20 times 1 over 1 plus x squared, which then we can now take the antiderivative, and we should see that this looks familiar, and e to the x is always e to the x. So if we do that, we get f of x equals e to the x plus 20 times the inverse of tan to the x plus c. Don't forget the c. F of x, f prime of x equals e to the x plus 20, 1 plus x squared minus 1. If of 0 equals -2. So we already solved for this part of it. Now, to find c, all we have to do is plug in 0 and set it equal to -2. So we can do f of 0 equals e to 0 plus 20 times inverse tan to 0 plus c equal to -2. Now e to the 0 is 1 plus inverse tan of 0 is 0, because when you think of a unit circle, it's 0 times 20, 0 times a number is 0. We get 0 plus c equals -2. Now we need to get c alone, which means c equals -3. Now, to get the final equation, we should plug it back in. So we get f of x equals e to x plus 20 times tan inverse of x minus 3.
Very good.
So in relation to example 3, this figure shows the graph of the function we just solved and its antiderivative. So we note that when f prime of x is greater than 0, f is always increasing. And when f prime of x has a max or min, f has an inflection point. The purpose of the figure is to mostly check on our calculations.
Oh. So the graphs of f and f primed, remember we learned way back in section 4.2 how to compare graphs of a function and its derivative. It's really the same thing that's going on when you look at a function and its antiderivative. It's just that the original plays the role of the derivative and the antiderivative plays the role of the original. So the slope of the antiderivative is the original. And you can use all the rules that we know about inflection points, mins, and maxes to check your work by graphing a function and its suspected antiderivative. If you're not sure if you've solved a question correctly, go ahead and graph the antiderivative and the original in Desmos and see if things line up the way they should between an original and its derivative. Just being mindful that the antiderivative now plays the role of the original and that the original now plays the role of the derivative. All right, I think Katie has a few more examples for us here. Oh, sorry, and I was watching this one earlier.
Now we're going to do example 4.
Now for example 4, you're going to find
Okay.
f to the prime 2, I don't know how to say that, equals 12x squared plus 6x minus 4, where f of 0 equals 4 and f of 1 equals 1. So we're gonna take this like one step at a time. We're gonna take the first antiderivative, which will be f prime x equals, we'll write it out step by step, so it's easy. It's 2 plus 1 over 2 plus 1 plus 6 times x 1 plus 1 over 1 plus 1 minus 4x. Since when you take a derivative, the variable goes away, plus c. Don't forget the c. Now to simplify this, you get f of x equals 12x cubed over 3 plus 6x squared over 2 minus 4. Fix it out. Minus 4x plus c. We can cancel those, which gives us f prime of x equals 4x cubed plus 3x squared minus 4x. Now, we're going to have to take the antiderivative again. So to mark where we're going to do that, I'm going to write again right here. So then we get f of x equals, I'm going to write it out step by step just so no one gets confused and that it's very clear to understand. Plus 3 times x2 plus 1 over 2 plus 1 minus 4x 1 plus 1 over plus 1 plus c x. Add the variable, and then we're going to add plus d because that's our new constant. So clean this up. F of x equals, we'll do 4x to the 4th over 4 plus 3x cubed over 3 minus 4x squared over 2 plus c of x plus d, our new constant. Now we can cancel these, simplify it, another cleanup, which will get x4 plus x cubed minus, that'll be 2x squared plus cx plus d. Now we can find d first because we're going to want to find the constant first. So to find d, we're going to do f of 0 equals 4. Use the first one that we were given. So if we do this, we do f of 0 equals 0 to the 4th plus 0 to the 3rd minus 2, 0 squared plus c times 0 plus d equals 4. When we do that, obviously we get 0, 0, 0, 0, which means d equals 4. Now we want to find c. And to do this, we'll use the second one that we were given. And if we plug that in, 1 equals 1 to the 4th plus 1 to the 3rd minus 2 times 1 squared plus c times 1 plus 4, since now we have to plug that in. And then we all set it equal to 1. This gives us 1 plus 1 minus 2 plus c plus 4 equals 1. We get c equals -3. And then that means our final equation, sorry, that wasn't there. Our final equation is going to be f of x equals x to the 4th plus x to the 3rd minus 2x squared minus 3x plus 4.
So that gives us our final answer. And moving on from that, so if we are given a graph of a function f, it seems reasonable that we should be able to sketch the graph of an antiderivative, capital F. So suppose we are given f of 0 equals 1. This gives us a point at 0, 1, and the derivative f prime of x equals f of x will show us which way we move our pencils in the stages of this derivative. And this is a place to start. And the next example, it will use the principles of this chapter to show how to graph f even when we don't have a formula for f. An example of this would be f of x is determined by experimental data. So for example 5, we're given this graph to the left, and we're going to make a rough draft of its antiderivative. We are also given f of 0 equals 2. And we know that the slope of y equals capital F of x is f of x. And we also have a point at 0, 2. Capital F is initially decreasing because f of x is negative when it's 0 less than x less than 1. I'll give time to write. We can.
So I'm gonna pause here just for a second to help you guys internalize this because it is a little bit tricky. We're given the graph of little f, and we want to sketch the graph of big F. And the idea is that precisely as Katie said here, the slope of big F is little f because little f is the derivative of big F. So if we look over here at x equals 0, we see that little f is negative down there, which means that big F is decreasing. In fact, everywhere from x equals 0 to x equals 1, little f is negative, which means everywhere from x equals 0 to x equals 1, big F will be decreasing. I'll let Katie take back over.
You can also see from the graph, if we look at these points 1 and 3, that f of 1 is also equal to f of 3, which are both equal to 0, which means that f has horizontal tangent lines when x equals 1 and x equals 3. Okay. Now, for 1 to x to 3, f of x is positive, as we can see on the graph, which means that f is increasing. We also see that f has a local minimum at x equals 1 and a local maximum at x equals 3. For x greater than 3, f of x is negative. So capital F is decreasing. If we were to write an interval, it'd be on 3 to infinity. Since f of x is approaching 0 as x is approaching infinity, the graph of f becomes flatter as x goes to infinity. Also notice that f double prime of x equals f of x. And from this, we can see that there's changes from positive to negative at x equals 2 because it goes from increasing to decreasing. And it does this change. Goes from positive to negative at x equals 2, and it goes from negative to positive at x equals 4, which means that there's points of inflections on f, capital F, at x equals 2 and x equals 4. So now we can take these and sketch it. We were first given that we have a point at 0, 2, so we can automatically do that. The next, we know that it's decreasing from 0 to 1 because we got that up here. We also know that there's a minimum at x equals 1 and a point of inflection at 2. So that means we can start going up, but it'll change concavity at 2. We are also told that there is a maximum at 3. Once we have that, then we can see that anything greater than 3, it is now decreasing because it was negative on f of x. And then it'll flatten out. So then we get this sketch. And to double check this, we can check the answer, which looks pretty close to what we got.
Alrighty, so this business of graphing capital F from little f is the same idea of trying to graph a function from its derivative. And we've played this game in the other direction in the past, trying to sketch the derivative from the graph of the original. So we're kind of turning all the differentiation stuff we did before on its head. And that makes sense given that this is anti-differentiation. I'm going to go ahead and play this last video to make sure we have enough time to get it done and questions at the end. Is there anything that you guys would like me to fill in or go deeper on so far? All right, then we'll go ahead and start this.
So now we're going to talk about rectilinear motion. Anti-differentiation is useful in analyzing the motion of an object moving in a straight line. We can recall that an object has a position function, s equals f of t, and the velocity function is v of t equals s prime of t. This means that the position function is an antiderivative of the velocity function. Likewise, the acceleration function is a of t equals v prime of t. So the velocity function is an antiderivative of the acceleration. If the acceleration and the initial values s of 0 and then v of 0 are known, then the position function can be found by antidifferentiation twice. Sorry for my pronunciation. So moving on to an example of this, I'll give you guys a second to write this down while I say it. But example 6 is a particle moves in a straight line and has acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals negative 6 centimeters per second, and its initial displacement is s of 0 equals 9 centimeters. Find its position function s of t. Well, for this, v prime of t equals a of t. So let's start by getting the first antiderivative. And we can do this by how we've been doing it this whole class. So v of t equals 6 times t 1 plus 1 over 1 plus 1 plus 4t plus c. Then we can clean it up by doing 6t squared over 2 plus 4t plus c, which then gives us v of t equals 3t squared plus 4t plus c. Now we are able to find c since v of 0 was given to us. V of 0 equals -6. So then we can plug it in, and it gives us 3 of 0 squared plus 4 of 0 plus c equals -6. And clearly, c will equal -6. Now, since we now have v of t, we can use this to get s of t because s prime of t equals v of t. So let's get the second antiderivative. We're going to do the same steps we did to get v of t, which will be 3 times t to the 2 plus 1 over 2 plus 1 plus 4 times t to the 1 plus 1 all over 1 plus 1 minus 6t since we plugged in the c plus d, our new constant. We can simplify this by crossing out the 3 over 3 and it leaves t cubed plus crossing out the 4 over 2, which leaves us with 2 squared minus 6t plus d gives us s of t. I'll give a second to catch up. So we also know that s of 0 equals 9. So we're going to plug in again and get 0 cubed plus 2 times 0 squared minus 6 times 0 plus our constant d equals 9, which gives us d equals 9. Now, to get our final, all we have to do is plug everything in, and we get s of t equals t cubed plus t squared minus 6t plus 9. So, as an introduction for the next example, we need to know that an object near the surface of the Earth is subject to a gravitational force that produces a downward acceleration denoted by g. For motion close to the ground, we may assume that g is a constant, its value being about 9.8 meters per second squared, or if you're using feet in your problem, then it's 32 feet per second squared. So we're going to move on to our last example. Example 7 says that a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Find its height above the ground t seconds later. When does it hit the ground? I'll give a second. So we know that motion is vertical. And since it's upwards, it's going to be positive. We also know at time t, the distance above the ground is s of t. We also know that the velocity v of t is decreasing. Therefore, the acceleration must be negative. So this will help us start. Now that we have our acceleration, we can write our equation as a of t equal to dv over d of t in relation to time equals -32 since we are using feet. We're going to take the antiderivative to get v of t. And this is the most easy one, so you just do v of t equals -32, t plus c are constant. And we know that v of 0 equals 48 feet per second. So v of 0 equals -32 times 0 plus c, which then gives us c equals 48. We can plug this back in to get our final v of t equation, which would be v of t equals negative 32t plus 48. And then the max height is when v of t equals 0. So we set it equal to 0. So 0 equals negative 32t plus 48, solving for t. And we get t equals 1.5 seconds. I'll leave this up so you guys have time. Moving on to the second part. Since s of t, write this down, since s of t equals v of t, we're going to take the antiderivative again to get s of t. So when we do that, using the same method we have been, we get negative 32 times t to the 1 plus 1 over 1 plus 1 plus 48t plus d equals negative 32 t squared over 2 plus 48t plus d. Then we can rewrite it and clean it as s of t equals negative 16 t squared plus 48t plus our constant d. We know that s of 0 equals 432. So without even plugging in, even though we can, we know that d will equal 432, which gives us our full equation for s of t, which is s of t equals negative 16 t squared plus 48t plus 432. This equation is good until the ball hits the ground when s of t equals 0. So when setting this equal to 0, we see that 0 equals negative 16t squared plus 48t plus 432. Now we can factor out a negative 16 of this to get t squared minus 3t minus 27. And realistically, 0 is divided by negative 16 to get rid of that, but we don't need to write that step out. So this actually does not factor nicely. So we're going to have to use the quadratic formula, which is t equals, I say, opposite of b, or negative b, plus or minus the square root of b squared minus 4ac, all over 2a. And when we plug in our factors, we get negative 3 plus or minus the square root of negative 3 squared minus 4 times 1 times negative 27, all over 2 times 1. When we simplify this a little more and do some calculations, we get t equals 3 plus or minus the square root of 9 plus 108 all over 2, which then goes to 3 plus or minus the square root of 117 all over 2. And we can take out a 9 from the 117, which gives us a 3 in front of the radical, giving us 3 plus or minus 3 square root 13 all over 2. And we know that time is not negative. So that gets rid of the plus or minus, and it leaves it to plus. So the ball hits the ground around 3 plus 3 square root 13 over 2, which is about 6.9 seconds. The graph above shows the position of the function of the ball from example 7. It shows the conclusion that we met, which is that the ball reaches a maximum after 1.5 seconds and it hits the ground around 6.9 seconds.
Alrighty. So thank you so much, Katie. I know that you put a lot of time into those videos, and I think they came out really nicely. I hope everybody got everything they were hoping to get out of them. I want to make one little comment on the kinematic stuff at the end, because these problems can be quite long, and it's possible to get a little bit lost. So the key things to remember, all of these kinematics / rectilinear motion problems. And just a little bit of vocab fun. Kinematics, think kinesthetic, think like things in motion. And rectilinear just means moving along a line. So the projectile or object in question here, just like all of the problems we addressed earlier in the semester, are moving along a straight line, either up and down or left and right. Is that you have your position, which is usually either x of t or s of t. This is the position function. And then you have your velocity, which is the derivative of your position. And then you have your acceleration, which is the derivative of velocity, or the second derivative, d squared over dt squared, of position. So this relationship that you differentiate to go from position to velocity, and you differentiate again to go from velocity to acceleration, can be read backwards as well. So this means that v of t is the antiderivative of a of t, and x of t is the antiderivative of v of t, which is the same thing as the second antiderivative of your acceleration. And a problem like the one Katie just worked, where you're given the acceleration function together with some initial conditions, and then asked to come up with or answer questions about the position function, are very common problems in physics. In fact, there's so much so the groundwork of physics that we do study them a little bit here in calculus. You'll see them separately in physics and in much more detail. But this is the key to remember, right? Is that these things can be thought of in either direction. You can start with your position and then get velocities or accelerations to answer questions about the change, the rate of change for that particle, or you can be given the acceleration or velocity and then anti-derive to answer questions about the position, like when did the ball hit the ground. So let's thank Katie for the wonderful work she did here today. Are there any questions you guys would like to ask, either Katie or myself, before we wrap up for the day? Yeah, definitely an excellent job there. I really enjoyed watching those. And I love the way you did the uncovering. It's clear that you spent a lot of time working on the screencast. It's very nicely done. Alrighty then, if there are not any questions, I will go ahead and conclude the lecture here for today. On Friday, I'm going to talk a little bit about how antiderivatives connect to integrals. We'll talk a little bit more about properties of the definite integral and how you can start trying to weave these seemingly disparate topics together. Again, I'm working to kind of regrade your exams because I was really unhappy with the statistics I got out of my non-honors class. So be patient with me a little bit later today. You will see the final, whether they're curved or not, grades up in Canvas for exam 2. If you have any questions or anything you need to talk about, you can always come see me in office hours. Otherwise, I will see you guys on Friday. Have a wonderful rest of your day.